Hello everyone. In this video we're going to be talking about polynomial rings, which are of great importance to studying Galois theory and field extensions and all that sort of stuff that we're building up to. So a polynomial ring takes a ring and then looks at the objects called polynomials, which I'm sure most of you have seen before. Um, and it basically studies their properties. So to start with, we start with R being a commutative ring, although for most of this we're going to deal with a field, but for now we're just going to deal with it being a commutative ring. Then we define the polynomial ring R, R bracket T, or I'll just say R of T, to be the set of polynomials which look like this. A sub n, T sub n, where all these A sub I come from R. So in other words, these are polynomials in the variable T with coefficients in R. Now there's a very precise way, or I guess there's many precise ways to sort of state this. So for example, in Lang's undergraduate algebra, which I'm roughly following as my source for these lectures. The way he sort of rigorously defines polynomials is as sort of infinite vectors which are zero, which have infinitely many zeros, and then a finite amount of non-zero terms, after which everything else is zero. So this is finite, and then everything after is infinitely zero. And then you sort of define your operations on here, and then you say, okay, you say t is equal to this element 0, 1, and then 0 is indefinitely after that. And then that sort of gives you a way to rigorously define R of t. However, I'm just going to sort of take R of t at face value here, because I'd rather not spend too much time on the nitty gritty and get to some more useful things. So now we're going to look at if R is a subring of S. So these are both commutative rings. Commutative. And then we have a map f sub s from S to S, which is given by essentially plugging in. So I should say, if we start with f being a polynomial in R of t, then we get an associated map f sub s, which is given by essentially plugging in x into the polynomial. So everywhere there's a t, then there's an x. And so x is an element of S, right? And then all these a sub i's are elements of R, which are also in S. So this whole thing is a well-defined expression in S. Okay, and we can do this for any polynomial. So given a fixed element in S, there is a ring homomorphism R of t to S, which sends f to f sub s of x. Oops. And the fact that this is a ring homomorphism essentially follows from, I mean, it's just using the ring structure of R of t, except everywhere there's a t, we now are plugging in x. So this is essentially saying that, you know, if we evaluate all the polynomials at x, of course it's going to obey the same sort of operations. However, this ring homomorphism can actually tell us some information about this element x. So, so we define R of x. So let me give a name. What name should I give to this map? I'm going to call it x star. So x star is the map which sends f to f sub s of x. And so I'm going to call R of x the image of x star. So this is a subring of S. So if R of t is isomorphic to R of x, which in another sense means that if this ring homomorphism is injective, or we could also say if it's an embedding, then we say x is transcendental. It's transcendental over R. So in other words, essentially x star, this evaluation map, if the image is giving us something that's isomorphic to our original polynomial ring, then you can kind of think of x acting as a variable over R. So the transcendental elements are sort of variables over R. And an equivalent, we'll see that in an equivalent way of looking at this is that there's no polynomial in R such that that f of x is 0. And in fact, this is immediately equivalent, right? So I said this is equivalent to saying that x star is injective, i.e. if f sub s of x is equal to 0. So if I get 0 from plugging x into some polynomial over R, then f must be the 0 polynomial. So there's no non-zero polynomial that when I plug in x, I get 0. So that's the sort of the typical way we define transcendental elements, right? So as an example, pi and e are transcendental over, say, I mean, you could say z or q or r, really, well, not r, but yeah, z or q. Yeah, so these both work since we're dealing with commutative rings. Square root of 2 is not transcendental. So even though, so here we might consider the example where R is Z and S is Q, right? Or rather, S is maybe R, right? But the real numbers are. So the element square root of 2 is an S, but not in R, right? So square root of 2 is not what's in the real numbers, but not in Z. Okay. But square root of 2 satisfies f satisfies this equation for f equal to t squared minus 2, which is an element of the polynomial ring over the integers, right? So the square root of 2 is not transcendental because there is some non-zero integer polynomial which admits a sort of essentially a root of square root of 2. Okie doke. So now we're going to deal with K being a field and F being an element of the polynomial ring over K. So let's say F is equal to A0 plus all the way up to A sub n, T sub n, with A sub n being non-zero. Then we say that the degree of F is equal to n. So the degree is the biggest index that you have a non-zero coefficient of your polynomial. By convention, so if A0, let's say F is just equal to A0, which is a constant but non-zero, then A0 is the biggest non-zero coefficient, so we would say the degree there is 0. However, the degree of F, which is the 0 polynomial, right? There is no non-zero coefficient, and so by convention we say that this is minus infinity, and we use the convention that if I take minus infinity plus anything, I get minus infinity. And so here, A is either A is either, you know, a non-infinite number, so I might write it like this, or A is equal to minus infinity. So I'm not looking at the case where A is positive infinity, and I'm and no other operations with minus infinity are defined. So this is kind of just like notation, where we need a minus infinity that kind of makes things work in a sense, with some of the theorems, just so that we don't have to deal with special cases where one of the polynomials is 0. And in particular, this is that the degree of a product is the sum of the degrees. So we notice if one of these is 0, if f is 0, say, then the degree here will be negative infinity. But 0 times g is also minus infinity. So so then it doesn't matter what this is, right? This plus minus infinity is going to give us minus infinity. So this works. On the other hand, this actually shows you that, you know, if this is greater than minus infinity, then these both also have to be greater than minus infinity, which implies in particular that k of t is an integral domain. Right? In other words, if fg was equal to 0, then the degree would be negative infinity. But if f and g were both non-zero, then these would be finite degrees, and we can't add up finite degrees and get minus infinity. So one of them has to be 0, which is saying that k of t is an integral domain. And the actual proof of this, of course, I didn't actually prove why this holds true, but you would let f equal something like this, and then G would equal something like this. B sub m T sub n, where A sub m and B sub m are non-zero. And then FG goes up to A sub n, B sub m, T to the n plus m, and this is non-zero, so the degree is n plus m. So I'm kind of like skipping over some probably some minor technical details, but these are some sort of tedious things that you can find in a textbook if you so desire, or carefully go through them yourself. Okay. So the next thing we want to do is look at the roots of polynomials. So i.e. x such that f of x equals 0. And again, the notation here is that f is a naught plus all the way to a and t sub n, and then we're defining f of x to be a0, and everywhere there's a t, we put an x instead. Okay. And the roots of polynomials is going to be essentially the guiding factor to Galois theory. So we're first going to start with a lemma that says we let f be in k of t and alpha be in k. And so whenever I write f is an element of k of t, I'm going to sort of implicitly have this this definition, unless like, and if there's like a g, then I'm going to have it with like b and a different degree, and so on, right? Then there exists C0 through Cn in K such that essentially I can write f as a polynomial in terms of t minus alpha. Okay. And the proof of this isn't hard. It's just something that we kind of want to separate from the main theorem. The proof is just to put, so we have f is a0 plus a n t to the n, and we let, or we don't let, but we write, put t equal to alpha plus t minus alpha, and use the binomial expansion. The binomial expansion is something that's well defined in any commutative ring, right? So we have the a plus b to the n is the sum over n choose r, a to the r, b to the n minus r, where r goes from 0 to n, and then the n choose r just sort of numbers, but in a commutative ring, remember that we have numbers given by a natural homomorphism, or really a natural embedding, well, not an embedding actually, a natural homomorphism from Z to R, right? Okay. And so really that's the lemma. Like if you wanted to write it out carefully, you could, but we don't really need to. So why is this important? Well, this is important because so note that f of alpha is in this new terminology, right? If I plug in alpha, then I'm going to have all the t minus alpha terms are going to be 0, so I just get c0. So if alpha is a root, which means f of alpha is 0, so I have c0 equals c0 equals 0, so I have f is c1 t minus alpha plus blah 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 plus c sub n t minus alpha to the n, and I can actually factor out a t minus alpha here, and I get c1 plus blah 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 c sub n t minus alpha to the n minus 1, and I get some other polynomial here. I don't particularly care what it is, but the important fact is that if I have a root alpha, then I can factor t minus alpha and get some other polynomial in my polynomial ring. So the theorem that we now show is that if f not equal to 0 has degree n, then f has at most n roots. And the idea is essentially by induction. So by induction on n, so if we have roots, distinct roots, so I should say at most n distinct roots here. We have n distinct roots, well not n, but we have distinct roots alpha 1 through alpha n plus 1, so I have more than n roots here. And then we let f equal t minus alpha 1 h of t. Well, I'll just write h. Then for I greater than 1, 0 is equal to f of alpha I, which is equal to alpha I minus alpha 1, which times h of alpha I. So since the roots are distinct, that means that this difference between the roots is non-zero. And since we said that k of t is an integral domain, that implies that this must be equal to 0. So h has n distinct roots. And so that shows by induction that we're going to have essentially, we started with a polynomial of degree n with n plus 1 distinct roots, and then we got from that or really more than n distinct roots, and then we got that from that a polynomial of degree n minus 1 with more than n minus 1 distinct roots. So by induction, we're eventually going to end up with a constant polynomial, a non-zero constant polynomial, which has no roots, and we're going to have that must have at least one root, and that's a contradiction. So induction gives a contradiction. Because there will be a non-zero constant C sub n which has a root. Okay, so that shows that a degree n polynomial can't have more than n distinct roots. So this is kind of similar to what is known as the fundamental theorem of algebra, which is kind of ironically named, at least in the grand scheme of how we ended up naming abstract algebra. So algebra was initially a name given to the subject of mathematics dealing with solving polynomial equations, and that's how you sort of learn it in high school. And so that's why the fundamental theorem of algebra was named the fundamental theorem of algebra, because it has to do with solving polynomials over the complex numbers. However, the complex numbers are an analytical construction, or I mean, you can think of them as an algebraic construction from R, which is analytic or topological, even if you prefer that standpoint. So there aren't any purely algebraic proofs of the fundamental theorem of algebra, which is ironic, but the reason is that really the fundamental theorem of algebra is not a statement about abstract algebra. It is a statement about the complex numbers, which are intrinsically analytical or topological, if you will. Okay. So a corollary to this is that if K is an infinite field, which we'll see why this is sort of an important distinction to make. I'm not going to talk about finite fields, mostly because they just kind of like mess with things, and like they're not hard to sort of study on your own once you get the general feel for field theory. So we're going to assume K is infinite, right? So it's at least countable, right? So K is an infinite field, and then F and G are polynomials over K. Then if F of C equals G of C for all C and K, then F equals G in the polynomial ring. So if all the evaluations over K are equal, then the two polynomials have to be equal. And I'll discuss briefly why this isn't true in a finite field. So to prove this is rather simple. F minus G has infinite roots. So it must be the zero polynomial. Right? Because we've just stated that if we have a finite dimensional polynomial, which is non-zero, then it has finitely many roots. But here, f minus g, if I plug in any value for in k, which I have infinitely many values, I get 0, because I get f of c minus g of c, which is 0. So I have infinitely many roots, which means that f minus g is 0. So why is this a distinction to make? Well, in finite fields, which have characteristic P, okay, so I proved in the video about ring characteristic that a field either has characteristic 0 or it has characteristic P for a prime number P. So it turns out that the rings with characteristic P are finite field. The fields with characteristic P are finite fields, and the rings with characteristic 0, well, obviously they have to be infinite because characteristic 0 means you have as a subring something isomorphic to Z. Z is infinite, so if you contain an infinite set, you must also be an infinite set. So in such fields, we proved the so-called freshman's dream, I guess, and we showed that this is true. And so clearly, this is some polynomial. I guess if you want, or I think t and t minus p are equal under evaluation. But not as polynomials, right? Because t and t to the p are different polynomials. Okay. So an example of this is, say, z mod 5z. So that would be a prime. So this is a finite field. Everything has an inverse. And so if I raise anything to the fifth power, I'm going to get back itself, right? So 2 to the fifth is 32. 32 mod 5 is 2. So I get 2, and then 3 to the fifth is 243, which is 3 mod 5, and then 4 to the fifth is 1024, which is 4 mod 5. So, and then obviously 0 and 1 satisfy this. So t to the fifth equals t everywhere on the field, but they're different as polynomials. So again, I'm going to sort of work only over infinite fields and not characteristic p, because the arguments are a little more technical, and I'm kind of going for like an undergrad class here. Although if you're in a grad class, you might consider Galois theory over finite fields as well. Okay, so I hope this video helped, and I'll see you in the next one.